Hello, so good morning once again, and welcome to my YouTube channel. And you can see I've already uploaded a lot of videos, video tutorials. So last time we talked about the basic plots in R for animal science, and also I had the simple data visualization in R for animal science. And if you wanted to learn more about how to work on how to run discrete statistics, this video is also right for you. But today we will try to have a short session of linear and multiple regression in animal science. So let's try to jump in to the code. So this is the R Studio. So I don't want to talk more about how to install R and R Studio because I have other tutorial for that. So this is again R, and this is where your environment is for your data set that you are working with. And this is basically the output of your plots. And here is where your codes are running. This is the basic R, and this is where you write your code. And if you don't have it right in here, you can just go to File and New File and just write your code there. Write your code. So for today's session, we will run a short data set and ran a simple linear modeling and multiple regression. So I already have made a code here, but I wanted just to run it one by one. So for that, I have here the data. So let's just load the data. So let's just do this data, name of data, and read TSB. And of course, the name of your file. So basically, the name of the file is data.csv. And there you go. You have 60 observations and 8 variables. So here is you have the control, which treatment, control and supplement. So basically, you have only treatment, control and supplement, and you have the animal ID. You have the sex, female and male, and age months from 6 to 12, I would say, months. And you have initial weight in terms of kilograms, final weight, feed intake, and just try to, with that, let's say you have here animal ID, and then let's create a new variable. So create a new variable. So this is I already showed you for my previous tutorial. So data, let's say data, and I'm gonna write it like gain weight, like after feeding the animal. So let's say GHT less of data, which is the final weight, less of data to initial weight. And there you go. Oh, what happened? Oh yeah, because we forget this one here. And now you have 9 variables. So now we created a new variable, which is gain weight. Like, let's try to do some kind of analysis for that. So let's say this again, we have to, this is in character, but I want to transpose this to factorial level. So here, just run it. Treatment as factor, which is already I showed you from a previous tutorial. Now you have factor with 2 levels, which is supplement and control. And the same thing for the sex. So you have also 2 levels, so male and female. And just a little bit of um, data visualization, let's say summary of data for the gain weight. So gain weight is, we have maximum of 27 kilograms, is 14 kilograms, and so on and so on. So let's try to do the modeling. So modeling is like which variables that is influencing to a certain variable. So I'm not gonna discuss that. I hope that this session is you already familiar with why you're running linear modeling and multiple regression. So linear modeling is you just need one predictor and one response variable. So in this case, we can say your response variable will be gain weight, and your predictor will be feed intake and also the age, the sex, and the treatment. So let's say this is like the output of the six matter in terms of gain weight. Does feed intake matters the gain weight, or is it the treatment? Is it the control? Is it this and that and that? So that's kind of your so here again, you need a predictor. Predictor, and you have the response variable. So again, when you do the modeling, I don't want to discuss this, but I think you should have already a prior background in that. So let's just do this like a full model. Now let's stick to linear modeling first. So for linear model, linear EIC stepwise. Oh, okay. Let's stick to this modeling. Okay, so I thought it should be first with a linear model and then the multiple linear model. Okay, so let's just stick to this one. Here is the simple modeling. So again, as I had said, that you need to have a predictor and response variable. So your response variable is, let's say, your weight gain, or we can call it also like independent variable and uh dependent variable. So in that case, dependent variable is weight gain. I'm gonna change that to gain. So the world, it's the gain weight. Yeah. So let's say the dependent, dependent because the weight gain, the gain weight, the weight gain is dependent to the feed intake, or maybe it's the age, or it's because of the treatment. So this is when you have this like one, this is like synthesis example of a linear model, because you only have one predictor and one of response variable, or you only have one independent variable and one dependent variable. So let's stick to this model one. Let's say model one is feed intake has an influence to gain weight. So let's just try that. So again, this is how you write a model. So let's say you can actually use model one. Model one is equal to this, the linear model, then your response variable. No, sometimes it shows how just have to click it, and the sign feed intake. It's not showing, but let's see. And data is equals to data. And close it and run it. So now you have your first model, and just run this linear model. And in order to, let me just clean that. So you have the summary of your model one. So when you see the summary of your model one, you have here the results. So it has a 0.00 p-value is 2 times even, but then and this is the intercept. But the feed intake is 0.5. It means that the feed intake is not there's no significant. But then if you look at the estimate, so when you try to look at the results modeling, you can always just go to estimate and p-value, which is 0.5. It means that feed intake is not significant too. So I think I've showed you this last time. So let me just open my previous code so that I don't have to write a lot of code. So let's say EDE. So this is a good thing in R because you can save the code and then just replace the code to the thing that you wanted to. This is the scatter plot. I think I've showed you the last time already, and this is exactly what happens to our data in here. So we say that our model one is not significant from 0.5. So you can actually verify that when you have the scatter plot. So feed intake, gain weight, and this I just have to run it. So as you can see here is that it's not significant because you can see a flat line. There's no linear correlation. There's no linear model that says that the higher the feed intake, the higher the gain weight. But in this case, you can only see that the 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 line is just flat. So even if you, let's say if you even if you feed, let's say this is kilograms, even if you like feed the cattle like 1.5 kilograms of feeds, and then it really doesn't matter if it's 3.515 because there's no correlation. So maybe there's some kind of mechanism for the cow or the cattle that even if you feed him a lot, it really doesn't matter how in terms of the wind. So which is doesn't make sense. So next time we will have to deal with actual data. So this is exactly what happens. Now let's do for a linear multiple modeling. So multiple linear regression is just you have a lot of projections, a lot, just one, two, three, or you can even have like more, I don't know, 20 vectors. But then when you have a lot of projections, the model it could be really hard to interpret. And again, it's important for you to know that you cannot use two um variables that are highly correlated. That is exactly why with my previous tutorial that you have some kind of how to run like like a correlation plot. So like when you have the variables that are highly correlated, you cannot use that in uh one model. So let's say for example age months and what else? Let's say other variable, let's say age in year. Then if age months and age year is highly correlated, then you cannot use, you can either just use age year or age month. So as long as it is not highly correlated. So this example of multiple multiple because you have a lot of predictors, multiple regression. Okay, so let's just run it. Now in this case, we're adding 8 months. Like, if it's uh makes sense that age is also a matter in terms of gain weight. So let's just run this model two. And again, our model two is let's say summary model two. So model two is the same age intake, it's 0.8. And see, if you noticed here that our first model feed intake is 0.5, but when you added another variable, now the feed intake becomes zero point 0.8. So that's exactly what happens when you are combining different variables. So this is also age month is also not uh, 0.1. It means that it's not significant. So let's say our p-value at 0.05, so it is higher than 0.05. It means that it is not highly it's not significant. But if you try to look at the estimate, so like this is the gain weight, so you need kind of this year age mounts in order to have like in 0.5 of age, you will have a gain weight of 8 kilograms, something like that. So let's try to look at for the visualize this. So let's say feed intake, I'm just gonna replace it. So this is a good thing in R because you can just copy the code and replace it and gain weight and just change this to feed intake. And let's see. So again, if you can see here that it really doesn't matter at all because you can see again it's plot and see it's just a little bit of increasing 0.1, which is also lower than if you try to look at the value here for the p-value is 0.1, which is lower compared to this 0.85, but it's not significant. But if you try to look at the result here of our scatter plot, so basically there is a little bit of a trend, like a pattern. See, it's like it's increasing a little bit, but here you can see when the age 6 at the same, it will tend to increase a little bit. So let's say from this is 10, this is probably 15. So this is probably put it like 13, let's say 12. So 12 kilograms at the age of 6, but then after 12 months, which is actually 1 year. So from 12 kilograms only to about 16. So let's say 4 kilograms in just 12 months, which is ridiculously very low, right? So that's exactly what happened here. That's why it's not significant. And let's try to look at here as well. So now we're adding feed intake, age months, and no, I want the whole. So now we're adding feed intake, age months, treatment, and then when you have more variable, you can just type like that. Okay, so let's just run this model, and our model tree is already in our environment. Now let's try to do like a summary of model tree. So let's try to look at a summary model tree. Oh, so here it it changes, but still sub treatment supplement. There's no such thing as significance for the treatment. So 0.1, 0.2, 0.08, which is still higher than 0.05 for the age months, and feed intake. So if you can try to understand that, I added one variable. So age months is reduced to 0.8, 0.08, which is a little bit here. It's age is 0.11. So see that the height, that's why when you have more variables in one model, it will somehow affect other variables. And then that's because it's better to when I do modeling, I usually just separate model. Let's say for example, for case in the context of forestry science, I would definitely have like category, like a group. So let's say tree density or forest structure, DBH height, and then so on and so on. But then it would be easy to interpret. And then you can have the species diversity. You can use Shannon index, Weiner, or whatever that is that corresponds to species diversity. And then you can just look at the p-value and estimate and stuff like that. So let's say this is the full model here. Again, if you remember about this EIC, I don't want to discuss about it, but this is just how to do the EIC. Just EIC, the Akaike information criterion, which is like you're just comparing two different models, no more than two, like several models. So, and again, for EIC, the lower the value of EIC, the best the model. Let's say, given this um models that we have right now, I would say model one, model two, model three, and run it. And here's your results. So basically, model one, you have 380, 379, and 3. So basically, model one has almost the same AIC, but then model two is 371, which is the smallest. So you can see that model two actually is the best fit. So it's the intake and age would matter a lot, I would say, but then put a feed intake and the control or the treatment doesn't really have an effect, which you can see that already in your previous plot that treatment has nothing to do with your gain weight. So in that case, there's no such thing as uh feed intake. So if you remember my previous tutorial when I showed you the summary of treatment, you can see here, I remember this. So see the treatment, the control in terms of the mean and the standard deviation. So you can see here that the control in terms of mean gain is 13 kilograms. The supplement is 14 kilograms, which is not really like, far from 13, which is, I would say that it's more or less the same. It's like 1 kilogram difference is not that big. So that is why here you can see that it's not, I would say there's the feed or the treatment has nothing to do with the gain weight. That is why when you added the feed intake and the treatment as our model tree is more or less the same EIC. So in that case, I would say the best model is model two, which is the age and the feed intake. So again, based on what we have right now, is we can say that feed intake and age would somehow, based on the data that we have, age matters, but in terms of significant level is not significant. But then you can see again the age that the higher the age a bit, the higher it will gain. But then it's again the p-value is 0. So there is so-called like ANOVA. So ANOVA is like just comparing the different models. So just type ANOVA and then model 1, 2, 3, and like that. It's not here. Model 3, sorry. Do that. Now you got it here. So it's just the sum of squares and stuff like that. The p-value as well is not the same. Yeah, I mean it's not significant. So I think that's how it is. But again, is we can where is I think I lost it. So modeling regression. So just try to go back to our previous model. So this is the full model actually. The treatment, age months, treatment, sex data. So this is the full model. It's trying to put everything at once. It means that we added, this is the 1, 2, 3, 4. We have 4 variables. So let's just put it this way, like model 4, because we have already model 4. So run it. Okay. Gain weight is not around because it's not available because it's the other way around. Gain weight. And you just have to run it like that. And model 4 is already there. And I'm just gonna just change this to model 4. Remove that because I don't need this ANOVA. I only need how do you call it? So let's just clean this a little bit so that we'll have an it's easy to understand. So let's say summary of model 4. So now let's try to look at it. Oh, okay, that's interesting. But it still there's no significance. So no significance for food intake, no significant for age, no significant for treatment, and 6 male and stuff like that. So which is for me is like, and if you try to use the model, so model, hmm, so model 4 is still not the best. It's even higher EIC. So I would go for model 2 is 378. So based on that, we can actually just, like, uh, do like this EIC model summary. Let me just double check this if it will work. So model summary, does it okay? And then there you have it. And then you can just, like save this. So let me just change that. This a mistake. Model summary and run it again. And then write that CSV model summary and then model summary dot CSV. And if you try to go back to your folder, there should be their model summary. I don't know if it's here. Here is our model summary. And then you cannot just report it already. So what I usually do is just go to my Excel and, just let's say, just change that and change in AIC. That's a change in AIC, for table ready for publication. So let's say this is 3 minus, or the smallest one, or let's say the minimum, just to make sure that we are doing the right thing here. So 0.66. Oh, it's 0. Probably not the best thing to do that. So let's just stick to this one. So our smallest is 379, right? So 379.75, 0.66. So in that case, if we try to, and then you just have to put it there, model variables, something like this. And our since it's rank 1, point 2, 2, and here is 3, and here is 4. So this our model 1 is feed intake. Feed intake. You can, and here is feed in take plus, what was that? Model 2 is age, you know, things like this. So age, and here is fitting take plus, was it sex something? Sex. And here is, I mean, if you want to make sure, you have to make sure that you're doing the right thing here. So again, model 1 is fitting take. So model 2 is age, okay, age, and treatment and then sex. Okay, that makes sense to us. So age here is treatment. Treatment, and here is, I'll just copy that to easily restore it right away. And let's say age intake, let's just put it this way. It's like say predators, just to make sure. Predators. And here is treatment. Treatment plus sex. And here you can just double check this one as. And there you go. Then you are good too. And let's say, what else? And rank. Now, if I would somehow rank that, I would just go to sort of A filter, custom sort, and I will say rank small to highest, and then just type this one here and put it in your word, and then you are good to go. Table 1, modeling selection using our this and that. And you can write whatever you want in your table caption. This is your privilege now. So your modeling procedure, I will just clean it. I will just, do like this, clean it a bit, and like this, change to 12, continue on. It really depends on what you want it to write, right? And this way I just do that like this, auto fit to window. Now I can just make it bold, and that's it. It means that here, mod metals, predictors, intake, EIC, change in EIC. So basically, you have your best model is just feed intake and age. And then I'm going to just report that. And you are kind of, just understand this a bit. So I think that's all for this modeling selection. So I hope you learned a lot today. And next is we will do the parametric, non-parametric, which is basically I should have done it before this because it's more of the ANOVA, the t-test, the parametric test, and if your data set does not follow the normality and the homogeneity of your data set, so that's why you end up in non-parametrics using the Kruskal-Wallis and the Mann-Whitney test. So, but then I think that's all for today, and we will try to jump to our next tutorial. So all right. So I hope you learned today, and I hope that you'll be able to now do your own using your own data set.